Welcome everyone to the next lecture on the numericals on the economic dispatch part 2. So this is Professor Vishal Maitre from Department of Electrical Engineering, Bharati Vidyapeeth deemed to be University College of Engineering, Pune. So in previous video, we have covered about the numericals which are related to economic dispatch part 1. I have given it part 1 and part 2. So in part 1, we have covered about the numericals related to economic dispatch for the incremental fuel cost, the change in the fuel cost with the sudden change in the demand. So we have observed the incremental rate, then we have studied if the inequality constraints are violated, then what necessary steps have to be taken. Now in this particular lecture, that is numerical on economic dispatch part 2, we are going to mainly study about the economic dispatch when there are limits on the generator and when we consider the losses in the network, transmission network. So in the previous video we have covered the economic dispatch without losses. So in today's video we will cover about the economic dispatch with losses and few other numericals related to incremental cost and how to do the analysis related to that. So let me first focus on few equations that we will be requiring for economic dispatch. Now we know that the equality constraints we usually consider for the load flow analysis and the power demand. So for these two cases, the power demand is going to be the equality constraints. And when we consider inequality constraints, we consider about the losses. We also consider about the limitation that are imposed on the generator. All these factors are going to impact with the help of inequality constraints. So let us start with the video lecture on this numerical and economic dispatch. So let us see the first numerical that is going to be related to the economic dispatch. Now let me focus you that this C term, whatever we are seeing here, these are different now as compared to yesterday's example or previous video lecture. So this C is going to be the objective function which is defined in terms of a quadratic equation which is going to be the input output characteristics obtained for the generating plant. So we can consider it either in terms of alpha. So this we can consider this as alpha, this as beta and this as gamma. So we are defining the three constants or the multipliers which we can say. You can have any notations. I'm considering this as alpha, you can say I, beta I pi plus gamma I pi square. So that is forming the quadratic equation. Now let us first see in the numerical what is the details given for this particular numerical. So first thing in this numerical we are going to study about the losses which are neglected and the generator limits. So we will start with the basic numericals like yesterday we have in previous lecture we have studied about. So let us first see without neglecting the losses and generator limits, and later on when we consider the system losses and the generator limits, how the system behavior is going to change. So let us see one by one. So in this particular numerical we have to find the optical dispatch and the total cost in dollars per hour for the three generators and the given load demand. So the three generators objective function is given in the form of quadratic equation which is C1 equal to 500 plus 5.3 P1 plus 0.004 P1 square. P1 is going to be the power term, real power term. So its objective function, the overall unit for that equation is dollars per megawatt hour. So this power whatever is there we are considering it in megawatt. Similarly for the second generating unit we have 400 plus 5.5 p2 plus 0.006 p2 square. C3 the third generating unit we have 200 plus 5.8 p3 plus 0.009 p3 square. So this is going to be the three generating units with the quadratic equation with that is the input output characteristics, and it has to satisfy the demand of 800 megawatt and we have to carry out the necessary optimal dispatch. So for that we need to calculate certain parameters. So first we are going to calculate the Lagrange's parameter, that is going to be Lagrange's multiplier, sorry, which is lambda, which we is summation of P demand with summation of I equal to 1 to the number of generators. Beta I, as I mentioned, that this is going to be the beta I, 5.3 for first generator, 5.5 for second generator, and 5.8 for third generator. And gamma is going to be these three terms: 0.004 gamma 1, 0.006 gamma 2, and 0.009 gamma 3. So these are the three gamma terms that we are going to consider. So divided by summation of I equal to 1 to n number of generators, 1 divided by 2 times gamma I. So this is the derivation which is there, we have covered in the previous video lectures. You can refer that. We are just using the formula and for solving the numerical. So we can substitute, as we know that the demand is 800. Now for first generator we have 5.3. We can refer these values. Then 2 gamma is actually 0.004 multiplied by 2, it becomes 0.008. Similarly for second generator we have 5.5 divided by 0.0012, which is multiplying by 2 with this particular term, that is gamma. So we get the second term, and the third term is for the third generating unit, 5.8 divided by 0.0018. We can see that 0.009 multiplied by 2, we get 0.0018. So which is reflecting here, divided by 1 upon the same terms which were there in this particular denominator. As there is 2 gamma I, so same terms will be here. So on solving this particular equation, we get the Lagrange's multiplier output as $8.5 per megawatt hour. Now this, we can use this multiplier for calculating the all power outputs for the three generating units. So the formula for that is Pi, that is for the respective generator power output, will be equal to lambda Lagrange's multiplier minus beta I upon 2 gamma I. So note down whatever is the constant term from the quadratic equation, we are neglecting it, or we are not using it in the calculation. Only we require this beta and gamma, so which are going to be helpful in calculation. So one by one we substitute lambda. Now we have 8.5 minus 5.3 divided by 2 into 0.004, we get as 400 megawatt. Similarly P2 is 5.5. When we substitute, we get 250 megawatt, and P3 beta is 5.8. When we substitute, we get 150 megawatt. Now when we take the summation of all the three generators, that is P1, P2 and P3, it should come out to be 800 megawatt. Then we can say that it is completely balanced. So this is the power demand output for to satisfy the 800 megawatt. Now you can see that as in the question itself, it was not mentioned what are the limits on the generator or any other limiting factor or constraint is there, it was not mentioned. So whatever the output we have got, that generator 1 is supplying 400 megawatt to satisfy 800 megawatt demand. The second generating unit is supplying 250 megawatt, and third generating unit is supplying 150 megawatt. So this is the overall contribution when we consider without limits, without any constraints. So this is the best example for the explanation of the concept when we consider the system without losses and without any limits on the generating units. So as we can see that the three generating units P1, P2, P3 are plotted in the graph. So in terms of incremental cost curves, we have drawn the curves. You can see that this is for the generating one, that is going to be 400 megawatt, which is the highest. So it is almost a linear and very close, almost close to, we can say, 90-degree. Then we can say P2 is 250 megawatt and third generating unit, and this is the system which is being operating. So this is the incremental cost when we consider the for the three cases G1, G2, G3 for the three generators and the overall system. So this graph will be helpful for us to understand in the easy way how to do the analysis for the three generators and the overall system. Let us see the second example. Now in the second example, little bit different from the first example. Now here as we have seen in the first example that we have neglected losses and the generator limits. Now in the second example we will neglect system losses, but we are considering the generator limits. So neglecting system losses, find the optimal dispatch and the total cost in dollars per hour for the three generators and the given load demand, and the certain generator limits are given. Now as we can see that the three objective function are already given the same similar like the first example. So this is the case. The demand has changed. Earlier it was 800, now it is 975 megawatt. And the three which we can see is about, you can see here these three generating units, 200, one is having 200 to 450, second generator is between 150 to 350, and the third is between 100 to 225. So let me first focus on this 500, 5.3 pi and 0.004 pi. As I've mentioned that the equation is Ci will be equal to alpha I plus beta I into pi plus gamma I pi square. So this is the equation that we are considering here. So this equation is going to be useful as the objective function. It is applicable for all the terms. So it will be easy for you now for you to understand that what is the parameters for beta and gamma. So the demand is 975 megawatt now. Now let us see how to approach this particular numerical. Now the first thing is calculation of the lambda parameter, that is the Lagrange's multiplier, is similar like P demand, that is going to be the demand which is required by the load plus summation of number of generators beta I divided by 2 times gamma I. Now you can refer this particular equation and relate this three generating objective function and obtain the values of beta 1, beta 2, beta 3, gamma 1, gamma 2, gamma 3 respectively for the three generating units. So here I can say that we have I equal to 1 to 3 because we have three generating units, beta I divided by 2 gamma I. Similarly, denominator is summation of 1 I equal to 1 to 3 generating units, 1 upon 2 gamma I. We substitute the value like as we have seen in previous example, only the difference is now instead of 800 we have now 975 megawatt. That will be equal to, when we do this calculation, now that calculation part you have to carry on, and when we do the calculation which comes out to be 9.163 per megawatt hour. Similarly, we will calculate the power which is given by lambda minus beta upon 2 gamma I. So pi will be equal to 9.16, which is this lambda minus 5.3. When we have this denominator factor, we get 483 megawatt. Similarly, P2 is 305 megawatt and P3 with 5.8 as used as beta, we get as 187 megawatt. Now, this is not the final answer yet because the certain restrictions were imposed, that is the constraints were imposed on all the three generators in terms of P1, P2, P3. So P1 is going to have the maximum, we can see it is 450, but here it is crossing out 450 and it reaches to 483. So what we are going to do is we are going to set it to its upper limit, that is 450 megawatt. Then for the second thing, second generator 350 megawatt, now we have obtained it is 3 is not 5 megawatt, so it has no problem, it is well within the limits. For the third generator it is higher limit is 225 and this is 187 megawatt, so it is within the limit. So here what we can say that this is creating a much problem. 483 megawatt is creating a problem because it is violating the limit. So what we have to do is we have to solve for the remaining two values, that is 305 megawatt and 187 megawatt. So we will use these two equations, we will form these two equations, again solve them. So we can see that now earlier the demand contribution was 975 including the first generator, Now we will remove that first generating unit. We will consider only the second and third. We will consider the higher limit, that is 350 and 225, which comes out to be 525 megawatt. When we take the summation of these, which comes out to be 525. Now when we solve this, we get the lambda. Now new value of lambda we have to use with the same formula. We get the value of new lambda. You can observe here, this lambda is obtained from this particular formula itself, that is the Lagrange's multiplier. So we get the value of lambda is 9.4. So again we will calculate only now P2 and P3 with values of lambda as 9.4. So we get, as you can see here, we get it as 315 megawatt, and P3 we get it as 210 megawatt. So this is the change modified after the constraints applied on the particular system. So you can observe here, it is now 315 megawatt. Earlier it was 305 megawatt. It is to compensate this additional load which is being satisfied because it is violating the limits. And the third generating unit, earlier it was 187, now it has increased to 210. So the first generating unit we have kept to 450 megawatts, so now it becomes 450 plus 315 plus 210. So summation of all these three is now 975. So if we check now again, 450 is within the limits for first generator, second is 315 within the limits, and 210 it is also within the limits. So this is how the optimal dispatch solution is obtained for balancing for the three loading units, for the three generating units. So this is going to be helpful. This is called as the optimal power flow analysis. So this method is applicable if there is the generator one or two generators are violating the limits, then the third generator has to be adjust the generation capacity itself so that it is within the limits and the generation is distributed from the remaining two generator units. So this is how is the working of the optimal power dispatch problem. So in this graph now we can observe the three generating units G1, G2, G3 incremental cost. So somewhat it is different. Now you can see that it is somewhere around 7.5. The limit is to 10. So this is in the terms of dollar. Now this cost is second generating units, its initial cost is less and it's lower. We can say that the lower end or the lower end is lower as compared to generator 1, but its higher end is also slightly less than as compared to generator 1. But for generator 3 the lower end for incremental cost is less and its higher end is also less, but with more amount of power which is being generated by generator G3. So this graph is clearly giving the analysis of the three generating units with the incremental cost and power. We can do the comparison easily. So this is what is beneficial for the analytical point of view with the generator limit. Now let's just see the last part, the third part in this particular topic, that is the optimal dispatch when we consider the limits on the generator as well as we consider the losses. So this is crucial now because we are considering the third case here with losses as well as the limits on generator. So for that I've considered an example where we are having fuel cost and the plant output limits. So again we are taking three generator units which is given as alpha 1 200, beta 1 7 and gamma 1 0.00 n. Similarly alpha 2 180, beta 2 6.3, gamma 2 0.009. Then third alpha 3 140, beta 3 6.8 and gamma 3 0.007. Now there are restrictions or the constraints, inequality constraints imposed on the generator now because of the transmission losses introduced in the system. So we have P1 which is in the lower range of 10 and higher range is 85. P2 for second generating the range is 10 to 80, and for third generating unit it is 10 to 70. So now the real power equation loss is given by the equation we have not now point not 218 P1 square plus point not 228 P2 square plus point not 179 P3 square. So these are using the loss coefficients that we will see in the next slide when we are solving this numerical, and the demand has to be satisfied with all the constraints and the losses as 150 megawatt. So this is going to be applicable for the losses calculation. Including the losses, we can have how to satisfy the demand. Now let us see the example here. It is somewhat different now. So this parameter is 1 upon 1 minus derivative of, or we can say it is 2 times this particular term, that is beta, that is the loss coefficient we can say. So this I will just mention here. This is these three terms are going to be the loss coefficient. So this, for the first generating unit we have now, which we can say that it is 1 upon 1 minus 0.00436. So when I multiply by 2, 0.00218, multiply this by 2, so we get 0.00436. In the numerator we have now 7. So this is 7 is going to be the beta 1, and plus 0.06 p1, that is the derivative we are taking with respect to p1. The numerator is going to be the derivative with respect with respect to p1. So this is 7 and 0.00 in the numerator, so that will be equal to, now as we are equating all the three coefficients for beta, loss coefficients will be equal. So the second is, now when you multiply this 0.00228 multiplied by 2, we get it as, sorry, we get it as 1 upon so it is 0.00456, so it is 1 upon 1 minus 2 times the loss coefficient for the second generating unit, which is 0.00228, and for the third multiplied by 6.3, that is the derivative of this particular term, 6.3 plus 0.00p2, and the third term is going to be related to this 0.00179 multiplied by 2, which comes out to be 0.00358. So it is 1 upon 1 minus 2 into loss coefficient of the third generating unit multiplied by, in the numerator, by the derivative of this particular function in terms of with respect to p3. So now we know that P1, P2, P3, that is the three generating unit, minus the demand is going to be equal to the loss that is going to be satisfied. So again, when we solve the value of P1, when you solve the value of P1 with this particular equations, or we can consider the lambda as multiplier, as we have done this particular calculation. So I have not done the calculation again, so you can consider this reference and calculate the value of P1, P2, P3, so which comes out to be 35.1 megawatt, P2 is 64.1 megawatt, and P3 is 52.5 megawatt. So the loss, when we get this P1, P2, P3 value, we substitute here, we get the loss which comes out to be 1.7 megawatt. So with this terms, when P1 is 35.1 megawatt, P2 is 64.1 megawatt, P3 is 52.5 megawatt, and P loss is 1.7 megawatt, and demand that time it satisfied the demand of 150 megawatt. So this is how the calculation has to be proceeded. So hope this has been understood. So let me conclude first till this part, that we have considered the three cases here. So in the three cases we have considered two parameters. One is losses, the transmission loss term, and the second is about the generator limits. So in the first case we have studied when there are no losses and there is no generator limits, and the second example we have considered when there is a generator limit but no losses, and the third we have considered when there are losses as well as there are the limits on the generators. So there can be any probability of any three cases, so you can, it will be easy for you to go through any of the case and apply the same when any kind of numerical is asked to you. So let us go a couple of numericals related to economic dispatch with incremental cost. So let me focus here on the incremental cost term. So now we have considering here the two units of the plants with the fuel cost of f1, which is given. Now f1 is the function that is going to be the objective function, as I've mentioned. Now this is going to be p1 square So this is going to be the quadratic equation, first quadratic equation, second quadratic equation for the second unit. So it is given by 0.8 by 2 p1 square plus 10 p1 plus 25. So it is given in rupees per hour, and f2 is 0.7 by 2 p2 square plus 6 p2 plus 20. It is also rupees in hour. Then the incremental cost. Now how to calculate the incremental cost is, we can have the Lagrange's multiplier, or we can define it by incremental cost term, which is calculated by lambda 1. We have to take the derivative of this function with respect to p1, so we get it as 0.8 p1 plus 10, which is now in rupees per, sorry, which is calculated in rupees per megawatt hour, and lambda 2 is calculated with respect to p2 in terms of derivative with respect to p2. So it is 0.7 p2 plus 6 rupees per megawatt hour. Now let us consider an case if the two units together supply a total of 220 megawatt, then P1 is 100 megawatt and P2 is 120 megawatt, will result in an incremental cost of. Now this P1 and P2 we have already considered as given in this particular case. So P1 is 100 and P2 is 120, so that the total demand is satisfied 220 megawatt. So this will result in incremental cost of, so when we substitute here 100 into 0.8, which comes out to be 80 plus 10, so this lambda 1 will be 90 rupees per megawatt hour, and lambda 2 when we substitute, instead of this p2 when we substitute 120, we get 84 plus 6, which comes out to be 90. So we can see here that lambda 1 is 90 as well as lambda 2 is 90 rupees per megawatt hour. So this implies that the incremental cost of both the unit will be the same, that is the cost of one extra megawatt of generator will be rupees 90 per megawatt hour. So that is what is applicable. Now with this, even though if lambda 1 and lambda 2 is equal, now let us find the actual objective function f1 by substituting the values of p1 here. So it is 0.8 by 2, instead of p1 we have p1 now 100, so 100 square plus 10 into 100 plus 25, which comes out to be 5025 rupees per hour. And for the second objective function, which is 0.7 by 2 p2, which is 120 square plus 6 into 120 plus 20, which comes out to be 5780 rupees per hour. Now here for the second function the rate is little bit more because of the two terms. One is going to be this quadratic equation and second is going to be the megawatt capacity, which is more. So the total cost of generator now is just the summation of these two, which comes out to be f1 plus f2. So 5025 plus 5780, which is 10,805 rupees per hour. So for this particular function of quadratic equation, if there are two generating units, so the total cost will be 10,805 rupees per hour. So this is how to calculate the cost of the generation when the cost is given, the power is known, the demand is known, and with the help of incremental rate we can calculate the total cost which is required for the generation. Now let us assume the second condition, that instead of, now we consider some other case. Now the total demand is 200, so we had taken p1 as 100 and p2 as 120. So let me highlight this. So total demand is 200, so p1 we had taken 100 and p2 we had taken 200. Now in the second case, let us consider p1 as 90 megawatt and p2 as 130 megawatt. So the total cost of each unit now with this substituted values, f1 is now 4165 when we substitute the value in this particular equation, because the function is going to be the same. So which comes out to be 0.8 by 290 square plus 10 into 90 plus 25, which is 4165 rupees per hour. And second function is 0.7 by 2 130 square plus 6 into 130 plus 20, which is 6175. So we can see here the total cost of generation now is 10,880. Now earlier when we consider 100 and 120, the cost was 10,805 rupees. Now when we consider P1 as 90 and P2 as 130, so the cost has been increased to 10,880. So when we take a difference between this 10,800 10,805 and 10,880. So the difference is about rupees 75, which is for each hour of operation with this non-optimal setting. So when we have this non-optimal setting, we have to bear additional cost of 75 rupees. Rather, if we implement this optimal condition, so there we will have reduced 75. So this is the process how we have to go on optimizing the result till the case when this cost is minimum. So that is what is the objective function. Similarly, it can be shown that the load is shared equally by the two units P1 and P2, which is 110 megawatt. Then the total cost is 10,880 rupees per hour. So this is same like this particular case. So this is when we can have multiple cases for P1 and P2 for optimization and final result is 10,805, which is the optimum result. So we can have the conclusion from that particular example related to incremental cost. Now let us consider the second example where we can consider the three generating units now and the fuel costs are given for them. So F1 is 0.8 by 2 P1 square plus 10 P1 plus 25 rupees per hour. Second generating unit is 0.7 by 2 P2 square plus 5 P2 plus 20 rupees per hour, and F3 is 0.95 by 2 P3 square plus 15 P3 plus 35 rupees per hour. Now the generator has limits as compared to previous example. There were no limits. So let us have now limits on the generators, which are given by 30 megawatt and 500 megawatt. Lower end is 30 megawatt, higher is 500 megawatt for first and second generator, and the third generator is 30 megawatt to 250 megawatt. So the total load that these units supply varies from 90 megawatt and 1250 megawatt. So when we take summation of all these three, 30 plus 30 plus 30, which is 90 megawatt, and 500 500 250, which is 1250 megawatt for overall system. So assuming that the three loads are operational all the time, we have to compute the economic operating setting as the load changes. So this should be the calculation point of view, that whenever there is all the three units are working and as the load is changing, we have to do the economic setting. So let us proceed how to do this calculation. Now the incremental cost, as I've mentioned, we can calculate it by lambda 1 lambda 2 lambda 3, which is the derivative with respect to that particular generating units. So first equation with respect to P1, second equation derivative with respect to P2, and third equation derivative with respect to P3. So we get 0.8 P1 plus 10 rupees per megawatt hour. Second equation we get 0.7 P2 plus 5 rupees per megawatt hour. Third, we get it as 0.95 P3 plus 15 rupees per megawatt hour. So to achieve the minimum cost, so the minimum load, the incremental cost units are. Now the incremental cost, we have considered the lower end, that is 30 30 30. So we will substitute here 30. So 0.8 by 2, 30 square plus 10, which is 34 rupees per megawatt hour. So for second generating unit, it is 0.7 by 2, 30 square plus 5, which comes out to be 26 rupees per megawatt hour. And for the third generator, we have 0.95 by 2, 30 square plus 15, which comes out to be 43.5 rupees per megawatt hour. So since units 1 and 3 have the incremental cost, so we can see here 1 and 3 is having more amount of cost. So since 1 and 3 have higher incremental cost, they must therefore operate at 30 megawatt each. The incremental cost during this time due to unit 2 will be equal to 26 rupees per megawatt hour. So with the generation of units 1 and 3 remaining constant, the generation of unit 2 is increased till its incremental cost is equal to that of unit 1, that is 34 rupees per megawatt hour. So this will be fixed until it reaches to the value of 34 with the change in load. So this is achieved when P2 is equal to 414286 megawatt at the total power of 101.4286. Now how to calculate this P2? We can calculate it from the previous example as we have seen. So that we can consider and do the calculation. So an increase in the total load beyond 101.4286 megawatt is shared now between unit 1 and 2 till their incremental cost is equal to that of the third unit, which is as 43.5 rupees per megawatt hour. This point is reached when P1 is 41.875 megawatt and P2 is 55 megawatt. So the total load that can be supplied at this point is now equal to 126.875. So from this point onwards, now the load is shared between the three units in such a way that the incremental cost of the all the units are same. Okay, so we can say that P1, P2, P3 is equal to 200, and 0.8 P1 plus 10 equal to 0.7 P2 plus 5. We are equating the two equations, lambda 1 equal to lambda 2, and we are equating the second and third one, that is 0.7 P2 plus 5 equal to 0.95 P3 plus 15. So we have three unknowns, three equations. So when we solve these three equations, we get P1 as 66.37 megawatt, P2 as 80 megawatt, and P3 as 50.63 megawatt. And an incremental cost, when we calculate lambda, we get it as 63.1 rupees per megawatt hour. So in a similar way, the economic dispatch for various other load settings can be computed. So depending on the number of generator operating, when one and first and second unit is operating, how much is the cost, when the second and third combination is operating, the limit has to be imposed, and when the first and third is applied, how is the limit applied. It is depending on the incremental cost value, which is the minimum value. So we have to do its optimum operation to reach the demand for respective generators. So at load of total load of 906.6964, unit 3 reaches its maximum load of 250 megawatt. So once it reaches maximum load of 250 megawatt, because we see that unit 3 is having only 250 megawatt capacity, so once it reaches that, then the generation of this unit is kept fixed, and the economic dispatch problems now involves the other two units now, which is generator 1 and 2. So for example, the total load is, suppose it is 1000 megawatt. We get the two equations now, which is P1 plus P2, which is now 1000 minus 250. 250 is for the third limit, which is imposed on the third generator, because we cannot exceed that limit. So now we have to equate the first and second. 0.8 P1 plus 10 equal to 0.7 P2 plus 5. So that is equated over here. So on solving the two equations, two unknowns, we get P1, which is 346.67 megawatt, and P2 as 403.33 megawatt, and an incremental cost will be 287.33 rupees per megawatt hour. So further, this has to be reached continued unit 2 till the unit 2 reaches its peak with a total of 1181.25. So further, any increase in the total must be supplied by unit 1, and the incremental cost will only be borne by this particular unit. So again, if it is reaching its limit, so that will be the we can say the last limit, beyond which we cannot operate three generators beyond that particular limit. So that is the total which we can satisfy of 1181.25. Now this we can observe it from the graph, the total power and the power generated. So we can see here how it is increasing linearly. Almost all three are increasing linearly till a particular point. Now as P3 is having the lower limit, we can observe here, we'll just highlight it over here. This is limit is only up to 250. So once it reaches 250, it has to maintain at 250. But the limits on the first and second generator now is 500. So it can go up to, we can see this variation at this particular point. There is a slight slope change at this particular point. It is because of the incremental cost. We have to get it at minimum rate. So that is why this nature we can observe, and at the end we can see that at 500 this particular is stopped. So beyond this, whatever is the generation, that cannot occur, because the limit has been imposed. Whatever the limits have been imposed, it has been exceeded the limit, so we cannot go beyond that particular limit. So hope you have understood whatever we have covered in this particular topic. So please go through the numerical. You can have practice more numerical with this particular information itself. You can do certain changes by your end, certain parameters you can change, and then for yourself understanding, you can observe what changes you can observe in the behavior of the system, and try to plot the graph for all calculations for particular numerical, so that it will be easy for you to do the analytical point of view, that which generator is having more incremental cost with more output, and vice versa, or depending, or how to have the optimum cost so that we have the maximum output with minimum incremental cost. So all these factors we have to consider when we are doing the optimal analysis, power flow analysis. So that is the reason why we study the economic dispatch for the fuel. When we consider, there are various cases we have considered with the generator limits, without generator limits, with losses, without losses. All these permutation combinations will be helpful for doing the analysis point of view from the output of maximum power and minimum fuel rate. So in case of any queries, you can post a comment, so I'll get back to you related with a solid answer for your question, so that your doubts will get cleared. Okay, thank you for this particular session. Hope you enjoyed it. Thank you.